Hello, hello, hello. Welcome back to another episode of Kerbal Space Programming. Cheers, Kevin here, and today I'm pretty excited. We're using algorithms to optimize our algorithms, which is the best kind of craziness. So here we have a lander, the Vanguard lander, which is going to put us on the moon. It's going to be amazing. And I want to quickly talk about why it looks the way that it does, because these engines, these are dumb engines to put on a small little craft like that. They are very inefficient. Look at the delta V that we get, 1,500 meters a second of delta V. If I take these off and put on a smart engine like the LV909, the wonderful engine that is short enough that the landing legs can fit and everything, we get to 2,300 meters a second of delta V. That is fantastic. That is wonderful. And in the atmosphere, it does not take off. It has too low of a thrust-to-weight ratio. It's perfect on the moon, but on Kerbal, not so much. This is a vacuum engine, and yeah, it's a problem. Now, that isn't a problem if we were just going to the moon, but we want to be able to test this thing here. And the reason for that is that we've done a little bit of stuff with suicide burns, we've done a little bit of stuff with hover scripts, but we need to tie that all together before this mission because we're going to be theoretically sending Kerbals. And the moon is cratery. We can't rely on things being flat. We may need to hover a little bit and try and shift our position until we find a good spot to land. So that's why we're using these stupidly overpowered engines on this relatively small craft. Even these the slightly more sane engines, unfortunately, are too tall for the landing legs, which is unfortunate. So today, what I want to do is I want to focus on that hover script part of the mission, because that's going to be kind of the final step. We'll probably do a suicide burn until we're some safety margin off the ground, and then we'll say, all right, now restrict our descent to 10 meters a second, or restrict it down to 5, and whatever, do some sort of rolling thing, whatever the case may be. So we've got this thing decked out, which is good. It's got this Reflectron on here just for testing. We won't be using that, but we want to go ahead and test that we can get consistent hover behavior, and particularly that we can change the hover behavior as well. So I have a very simple PID loop set up here, and let's go ahead and just throw this on Launchpad and watch it go. So there we go. This thing is launched all on its own because it's got a script to do that, and its target is to accelerate at a rate of 20 meters a second. To go up at 20 meters per second. And the way that we're doing that is with a PID control. Now, if you remember, PID controls are a system for you give it some sort of error, and you ask it for some sort of output. And then you tune the values to try and reduce the error. It wants there to be no error. And there are 3 components to that. One is the proportional control. This is hey, I want to be driving at 65 miles an hour, but I am driving at 5 miles an hour. I'm going to floor the accelerator. There is the integral term, which if you're driving a car is, hey, my car slightly tilts to the left no matter what I do. The steering is just a little bit off. So I'm going to constantly apply a little bit of rightward steering to correct for that long-term problem. And then there's the derivative term, which is, hey, I'm accelerating super, super fast. I'm going to hit my target at 65 miles an hour right away. Maybe I'm going to back off the accelerator just a little bit. It sort of dampens based on the rate of change in the error. So this is what we're using here. Now, in the past, we actually wrote it ourselves, but now there is an alternative, which is very, very cool. Of course, temperature overlay enables because I've got hotkeys that are doing weird stuff. But here we have the documentation for the KOS PID loop, which we created on our own, but we're going to go ahead and use this here. So you can pass in tuning values to say how much does that direct proportional control matter, how much does that long-term integral error matter, and how much does the rate of change matter. You can give these values from 0 to 1. You can set a minimum output and a maximum output, which are very helpful because they also restrict when the integral term matters. There's an issue called integral windup, which if you imagine you set your thermostat, right? Your thermostat's supposed to set it at 65 degrees, but when you turn it on, it's 90 degrees outside. So it's going to take some time to get down to about 65 degrees. And so if your integral is just tracking how much total error there is across the entirety of time, it's going to get a little, it's going to say, hey, we need to overcompensate and make things way, way, way too cool, and it's going to take a very long time for that to wind down. This actually clamps that so that it reduces that. Oh, yeah, and then our little thing is over there. Yep, good job, us. This thing, maintained a decent rate, but all right, there we go. This is using one of those PID controllers, so good job. And it's staged, and our Kerbal will presumably fall back to safety, but we're going to end up reverting to launch anyway, because this is for testing purposes. So I'm going to jump over to the code real quick. Oh, I'm in the wrong file. Come with me, please. Thank you. Yes, so this demo code, this is how simple our PID controller is now. It was much more complicated when we did it ourselves. We say, all right, I'm going to create a variable called PID throttle. I'll set it to 0 just for now. I'm going to lock the throttle to PID throttle, so now I know I can just update that variable, and then the throttle will adjust to match it. I lock the steering to up and set the pilot main throttle, the manual throttle to 0 as per usual. I'll go ahead and stage, and then here's the actual PID loop stuff. So I create a PID loop, and I say local PID is PID loop, and I pass it these values. So I say I want the proportional control to matter 0.05 much, and I want the integral control to matter 0.01 much, and the derivative control to matter 0.01 much. And then I want these values to be bounded between 0 and 1. I want the output to be between 0 and 1 because, hey, that's what the throttle has to be. It's got to be between those values. Then I give it a set point. So I say, hey, PID, here is the value that I expect. I expect 20. That is the rate that is the amount of meters per second that I want. And so that is where your set point is. And then all I have is here, until we're out of fuel, continue to update the PID throttle variable by saying PID update, and I give it the current time. And then I say ship vertical speed. So that's whatever our current speed, vertical speed happens to be. So when we're on the, right on the launch pad, it was 0. And so it's going, hey, well, the set point is 0, so I better floor it. Once we start to crawl up and we're rising at 15 meters a second, then it pulls that down a little bit. But one of the things that is really frustrating about PID controllers is actually trying to tune them, trying to figure out the appropriate values to put in for these proportional and integral and derivative terms. And I don't want to do that. Algorithms are supposed to make life easy. And this just adds some additional stuff that I have to worry about. So obviously, the brilliant solution is to add another algorithm to fix this algorithm for us. I want to tune these 3 values, and I want an algorithm to do that. And of course, we happen to have one lying around. It is the genetic algorithm, which I've updated just a little bit. Brought kind of to contemporary stuff with our code. We used this to figure out the optimal ascent profile, and it did incredibly well, if I do say so myself. It's just, the algorithm worked particularly well. It's nothing to do with my code. But I've gone ahead and updated this, and I think it's a little bit clearer now. So here's the main loop. We say until false, evaluate some chromosomes. Chromosomes are just 0s and 1s. And of course, we're going to convert them into actual numbers, and then give it some sort of score based on some criteria. Then we're going to say, all right, now we have scores to rank how good a candidate solution is. We're going to go ahead and select some of them to be parents for the next generation. That's largely based on their performance, but it is a little bit based on randomness as well. If you have a very even spread, then it's close to just a random pick. So if you have someone who gets, if you have 2 competing guys and one of them got one of them got a 5 and the other one got a 5.1, it's not going to be, oh, well, the 5.1 is always the parent for the next generation. Then we go ahead and we cross them. So we combine solutions, and then we mutate them, which means we add a little bit of variation just to make sure that nothing gets too stuck. And then that becomes the new generation. And then we just continue that forever and ever and ever and ever and ever and ever and ever. Now, I've got a whole bunch of functions that actually do this. And in fact, this goes ahead and it stores out a whole bunch of data. We've updated this mainly because there are some issues, like we were using some hack to get access to a quote character so that we could log things out. We could log out TurboScript code to a file so we could run it, so we could save things between reverts. That's not necessary anymore because we can write JSON and read JSON, which is super, super awesome. So we can just go ahead and store things willy-nilly. It's all very, very convenient. So we've got all this stuff to load store data and blah, 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 blah. I'm not going to go too far into this because it is a lot of repeat. If you're interested in the code, go ahead and take a look on GitHub. This will all be up there. The only kind of significant changes we had in the past, this very complicated float library, and actually that still exists here. I think it's still in here. Yeah. Yes. Go away. Where we convert these strings of 0s and 1s to a number. And we used a crazy standard, the IEEE 754 floating point, 32-bit floating point signed standard thing, which is a lot of math and a lot of confusingness. In particular, it means that it splits up the ones and zeros into chunks of like, this is an exponent and this is the regular part and this is the sign bit that goes from positive to negative. What that meant is that when you're combining solutions, you end up with a lot of real craziness. It's very easy to accidentally mutate and go like, oh, we're just going to add some small change to this one solution. And it goes from being infinity it goes from being like a very large number to all of a sudden being a very tiny number, or being a negative number, or just going all sorts of crazy because of the way that this works out. So instead, I've gone ahead and just simplified and said we're not going to do that anymore. In the genetics library, we're not using float. We're just going to go ahead and we're using plain old integers. So, 911. So this value is going to be 3, etc. They're still 32 bits long. But what this means is that any small mutation or anything is going to make a lot more sense. We're not going to have crazy fluctuations between values. And it does mean that now everything that you get back is going to be a value between 0 and 1. And then it's just going to be the fitness function's job to go, all right, I'm going to figure out how to use that. Maybe if I need something that's positive or negative, I'll go, hey, all right, if it's less than a half, then that's negative or whatever. So that's a small change. Again, not going to go too far into this. Let's look at the actual boot file via which we can start testing out our PID control stuff. So here is the actual usage of genetics. I've gone ahead and I'm running Canoe, which is our library to give us import and export. And then I go ahead and I import our genetics library and we say genetics seek. And then I pass it a lexicon to define all of this stuff. And I say, here is where you can store all of the information about this project. Go ahead and store it to vanguard.json. And please auto-revert every time that you get a fitness value back from me. Then I give it arity. Arity is a fancy word in software development. It doesn't really matter. If I have a function and it takes 2 arguments, then its arity is 2. If I have a function that takes 1 argument, its arity is 1. If I have a function that doesn't take arguments, its arity is 0. All that I'm talking about here with the genetic algorithm is saying, hey, how many different numbers do I need to tune? And in this case, I need 3. I need the tuning values for the integral, the derivative, and the proportional term for the PID control. Then I give it a size. I say, here are the amount of solutions I want you to look at in a generation before you do all that merging and mutating and all of that stuff. And then I give it a fitness function. Now, ideally, I'd like to give it a fitness function like this. Params, parameter data. And data comes in as a list of those 3 values. And then I'll just return some score. But because I'm locking steering as part of this, I can't use, there we go. I can't use anonymous functions at the moment, although that has been fixed. There is a Dunbaratu, the wonderful KOS dev, has gone ahead and fixed it. It is up there. There is a pull request up on the repository. If you want to go ahead and work off of his branch, you're welcome to do so. But we will be waiting until it ends up making its way into release, which may be, there may be a bug fix release, or it may be that we have to wait until KSP 1.2. We will have to see. So, but anyway, the fitness function is now down here. We take in parameter K, which has just got those 3 values, and I've got it displaying stuff to the screen. And then from down here, this all should look pretty darn similar. We're locking the steering to PID throttle, locking the throttle to PID throttle, locking the steering to up, creating a PID loop, although we're creating it now with the values that the genetic algorithm gives us. And now down here, now we're really going to try and put this thing through its paces. All right, so we're going to say, your set point is 40. So I want you to rise at 40 meters a second. Once we get past 10 seconds, then I want your set point to be 0. So I want you to hover. I want you to have no vertical speed. Also, if after 10 seconds you find yourself below 50 meters a second, 50 meters off the ground, then stop immediately and you get a score of 0. So this is a very bad solution. Don't try it again. After 20 seconds, we're going to try and descend at a rate of -5. Descend at a rate of 5. So ascend at -5. I don't know. Then hover again, then go back up to 5, and then go to 0. And the reason for this is that we want to track not just whether this thing can maintain a particular rate of ascent, but whether it can change reasonably between different rates of ascent and how long it takes to settle in. We're also going to, so then we do the PID update thing, and then we're also tracking the total amount of error, and we're not subtracting for negative error. In fact, we are adding negative error, so we're taking the absolute value of the error that the PID controller finds, so that basically we want to look at any variance off of the goal. So if your set point is 0 and you're going up at 1, and then you go down to -1, then you go up to 1 again, then you go down. No, that doesn't even out We want you to be exactly on the target. Now, of course, we don't expect anybody to have a total error of 0, but that's, that'd be nice if it just so happened to happen. Anyway, so that is the loop. This is only going to run for 60 seconds because it's important because we're running a whole bunch of these. We want to make sure we can get through a couple of generations because it took a very long time when we were doing stuff with our launch profile because that required 5 minutes for each launch. And then we're returning a Gaussian, which is just a bell curve. We're saying, what's the total error? We want it to be 0. That's the center of the bell curve. And then we're making it very, very wide. So 250 is the middle point for that. And then there's the Gaussian function, which is just boring math. But anyway, that's enough code. Let's go ahead and take a look at this thing in action. And here we are on the launch pad. This thing should be generating some chromosomes, at which point it should find the first one. There we go. Generation 1 out of 25. And you can see the values that it has chosen, 0.73, 0.74, and 0.24. You see, yep, it is very, very wobbly. It's, let's see. So it's past its 40 mark, and now it's supposed to be hovering. And yeah, it's varying between 0 and 1. It's going a little bit above 1 now. Oh boy, that's going... Oh, no. Now, okay, so now it's moved on to the -5 meter a second stage, although it is overshooting that, I do believe. At which point now it should try and hover again, and then do its ascent. So basically, by adding all of these additional... By forcing it to try these various different steps, we're making sure that this is resilient to rapid changes, because this is something that we might expect on the moon, that we go, yeah, hold off a second because you are coming down on a slope, so go to hover and then shift over a little bit to the right, and oh no, you're going to crash into something, please, ascend at 5 meters a second or whatever. And of course, now that this is 60 seconds over, it returned a score, which means that this thing can go ahead and revert right away, which is fantastic. And now when it looks back, it's still generation 1, but now it is number 2. And the way that this is doing it is the genetic algorithm is saving out a dictionary so that if it ever encounters a chromosome that it has seen before, it goes, hey, I know that one. I know how that works. Here's the score for that. So that's how this is going. Let's go ahead and... Yeah, so this one... all right, so we're targeting -5. Unfortunately, the surface speed is a little bit suspect. Because, well, I suppose we should, probably ought to have put a Kerbal engineer on here so we could see exactly how that is doing. Because this does involve lateral velocity too, and there is a little bit of that because this isn't entirely centered because of because that thing sticks out, and so over time this thing will drift a tiny little bit. But this seems to be no, this is not doing a good job of staying at 0. Yeah, that's supposed to be at 0, but it is not. Well, okay, now there we're... Okay, yeah, looking up here, this is better. Well, we'll see. Okay. That is step number 2. While this continues to run, because I'm going to go ahead and run this a whole bunch in the background, let's jump back over to the code and take a look at what it has generated for us. So that's step 3. And we can see here, if I go ahead and refresh, it's created a new file on the archive called vanguard.json. I can go ahead and take a look here. The lack of noise makes me nervous. We'll close that. And you can see it's got a list of all these chromosomes, so it's got all of the items. And actually, yeah, no, this is fine. No, actually, I'm going to close out, and then I'm just going to open it up again. But read only, just because I don't want KSP to have any trouble writing to it. There we go. Oh, no. Thank you. So we've got entries, and of course there are 25 of these, so it goes down for quite a while. And those are just the ones that it knows are in the current generation. And then we see here it's got a list of what was the best score. And here is the generation that it got. And it should also list the best, and there it is, the best item down here. And it shows us the values that it used. So it looks like that was probably the second one that it tried, the 0.8, 0.88, and 0.2 for the tuning values. And that was the best one that it has found thus far. And it is keeping this list of scores, which will persist across generations. And yeah, so I guess we've jumped to generation 4 over in KSP world. And so yeah, here we can see all of the entries that it knows about. And in fact, if I close this up and then load it up again, we go down. Yep, there we go. There's the third one. So it has, okay, if I ever see this one, here's the score for that. If I ever see this one, here's the score for that. And I guess, yeah, so now it has a new best, 0.66. And that now means a much higher proportional control, a high integral control, and a very low derivative control. So that is interesting. And now we have all of this stuff logged out, and it should go a lot faster because if it ever finds duplicates, which was a bit of a problem with the launch profile stuff, it's not going to bother going through them again because there's no need to. Because it has this whole dictionary of, hey, I know what that results in. So yeah, if we jump back over here, we can see how's this doing. Yeah, okay, it's targeting. Yeah, it's hard to make it out just from here. So we'll really have to just trust the program to figure it out for us. But of course, this is all Generation 1, and that's really boring. So we've got to jump ahead and see what happens on Generation something in the future. Although, of course, it is going to take me 25 minutes, approximately, for each generation. So I'm not going to make you watch all of that. We will jump back in when we have more interesting combinations of cool solutions. So I was expecting this to be exciting. I was expecting this to be somewhat like our previous launch attempts, where all of, the ship goes from not very pointed towards space to very pointed towards space and figures out a wonderful ascent profile and becomes amazing. Yeah, this turns out to be way less exciting, and I was perhaps overly optimistic. In fact, I did record a whole bunch of footage. I let this thing run for about a little over 24 hours because I still need to make sure that this gets up on time. But I let this thing run for quite a while, and I'm not even going to show you the intermediary generations because there was not much change. We're still just dealing with boring, yeah, this sort of works type of solutions. As you see here, we're creeping our way up to Generation 50, which is the point where I decided, all right, cut it off. We've got to actually record stuff so that we can get this video up on time. So I'm going to jump over now. Let's we'll cut away from this, and we'll take a look at the data that we got out. So here is the Vanguard.json, the results. We've got these chromosomes that it was going to run for Generation 50. And if we go down here, we see these are not saved in a particularly helpful order. We see the best score that it found was 0.72. And I was keeping an eye on this over the course of generations. I think we were at like 0.71 around Generation 13. So it doesn't feel like we really improved much. Generation is listed as 49 because I actually cut this off while it was running the first one of Generation 50. And then we have all of these scores. So all of these various chromosomes and the scores that they happen to get. Now, it is possible that if we reran these, the scores would be a little bit different because physics and KSP and various stuff like that. But hey, we were trying to save some time. We ended up with, if we go down here, I ended up counting, not manually, but I ended up looking at how many of these we ended up with. We ended up with 820, roughly, solutions and their scores. Now, that's shy of what you would expect if we ran 50 generations and 25 things per generation, but we have to keep in mind that sometimes there are duplicate answers. And so when we reach a duplicate answer, we're not adding anything new to the dictionary. So if a generation just happens to copy something over, well, then we don't have to run it. We save a little bit of time. So we ended up shy of the, 1,250 that you would expect. And of course, yeah, there's some extra metadata in there just to help. That's just part of KOS. So the best score, and here's the best option that it found. And this is a KP value of 0.23, an integral value of 0.96, and a derivative value of almost nothing. I am not very confident in this, but okay. The other thing that I've done is I've gone ahead and extracted all of this. All of these, not these, but all the score values. And I wrote a little quick script. I just copied and pasted them in here using Ruby. That doesn't matter. I went ahead and created a data file where I took the chromosomes and pulled out the KP, KI, and KD values along with the fitness score, which gives us this wonderful CSV, which I've uploaded now to Google Sheets. So we can go ahead and take a look at that in a not ugly form. So, okay, here we are. If we go up to the, okay, yep, as I said, about 820-ish lines, chromosome, the fitness, the KP, the KI, and the KD. Now, because lexicons happen to be ordered, when you add something, it ends up appending it to the end, we should be able to see a trend, ideally, over the course of this. So if I go ahead and say, let's add a chart, we'll insert a chart. I may need to unzoom this, but okay. Here we go. This is a histogram of fitness, which is just frequency of scores in this range, which that's not what we want. We want to see the trends over time. I think this is probably close to it. Yeah, I think that's a time series. You can see here, yeah, no. There's really no marked improvement at all over the course of adding these. This is not by generation, but it's by when we add stuff to the dictionary. So ideally you'd see some sort of like, yeah, when we started off it was iffy, but then we got more consistently higher scores. Doesn't seem to be the case. So that's unfortunate. Do we at least see, and yeah, I need to figure out what's up with the key bindings here because it will not let me scroll to the top. Okay, do we at least see a correlation between fitness and our KP, the tuning value that we use for the proportional control? Let us take a look. We'll create another chart. And look, it gives us a scatter plot. Perfect. Let's customize that and see if we'll have it build us a fit line, right? Yeah, maximize this. Make it larger. Oh boy, that is a fun scatter plot. Yeah, give me a trend line, a linear trend line. Yeah. So not much correlation there. Can we get a, yeah, presumably not with exponential. Yeah, so basically all of this tells us that it thinks that generally increasing our KP is going to improve stuff. But of course, that's not even the one that got the best score had a very low KP. It had 0.2 something. So it was down around here. So basically the results are that we did not converge on anything, which is unfortunate. But hey, it's bound to happen. I think we will definitely have to do some manual tuning on our own. I think we'll look at some of the tried and true methods of trying to do that in the future. I may end up going ahead and letting this run for a while and just seeing if it happens to stumble on a solution and then, converge. But I suspect that after 50 generations and we're seeing absolutely no improvement whatsoever, that this test is just not. It could be that. Remember that kind of regardless of what you're using to solve these sorts of problems, if you have kind of a rocky terrain, like imagine we've used the example of hill climbing before, and try and find the tallest place on the mountain. Genetic algorithms are kind of a different form of hill climbing, but they're solving the same type of problem of finding global optimum. If you have a really, really, really bumpy map, then it's going to be very difficult to go, oh, yeah, this is obviously an improvement, let's trend in that direction, because there are going to be a whole bunch of different options that are vying for that, and it may be very difficult to tell the difference between a good solution and a better one. So, alas, as much as I would love to be all yay genetic algorithms, this seems to be one case where it just does not work. So we will have to revisit this and actually do the tuning, do the actual work in a future episode, and I will hope to see you then. Cheers.